Hello, this is video number 20 on my single variable calculus 2. In this video, we're going to talk about infinite series. A series is a sum of terms of a sequence. And here we are going to talk about only infinite series that involve infinitely many terms. This sum can be evaluated by taking the limit of partial sums. The nth partial sum is the sum of the first n terms of a sequence. S sub n, which is the nth partial sum, is a1 plus a2 all the way to an. Let's look at one example. Consider the series sum of 1 over 2 to the power of n when n goes from 1 to infinity. We want to find the first three partial sums. So the first partial sum is just 1 over 2. The second one is 1 over 2 plus 1 over 4, so 3/4. The third one is 1 over 2 plus 1 over 4 plus 1 over 8, which is the same as the previous one plus 1 over 8, and that gives us 7 over 8. The second part of the problem is asking us to find the formula for the nth partial sum. Now, if you look at this sum, these are terms of a geometric sequence. So we know how to find the sum of terms of a geometric sequence. So the sum of the first, second, all the way to nth term of a geometric sum is the first term minus the term after last divided by 1 minus common ratio. So the formula is first term minus after last divided by 1 minus common ratio. And we can evaluate this one by 1 minus 1/2 at the bottom comes to the numerator. We get 2 times 1/2 minus 1 over 2 to the power of n plus 1, which gives us 1 minus 2 over 2 to the power of n plus 1, and that simplifies to 1 minus 1 over 2 to the power of n. So this is the nth partial sum. The next part is find the infinite sum. So how do we find the infinite sum? Well, the sum of 1 over 2 to the n equals 1 to infinity, is the limit of these partial sums. So limit of 1 minus 1 over 2 to the power of n. Well, 1 goes to 1. 1 over 2 to the power of n is 1 over infinity, which is 0. So the answer to this infinite sum is in fact 1. Let's look at the next example. Determine if this series converges. If it does, find its value. This is the second type of sum that we can evaluate. This is called a telescoping sum. The way we solve this one is by using partial fractions. So we take this one, we factor the denominator, and we write it down as a over n plus b over n plus 1. We clear the denominators, we get 1 equals a times n plus 1 plus b times n. Then we plug in different values of n equals 0 gives us a equals 1, n equals negative 1 gives us 1 equals b times negative 1. So b is equal to negative 1. So in other words, we can write down the sum n equals 1 to infinity of 1 over n squared plus n, which is the sum that they gave us, as the sum of 1 over n minus 1 over n plus 1, n equals 1 to infinity. Let's write down the first few terms and then you'll see what happens. The first term is 1 over 1 minus 1 over 2. The next term is 1 over 2 minus 1 over 3. The next term is 1 over 3 minus 1 over 4. And the next term is 1 over 4 minus 1 over 5, etc. So what is this infinite sum? As you see, this term and this term cancel. This term and this term cancel. This one and this one cancel, etc. So basically everything cancels except for the very first term. So the infinite sum is in fact 1. Let's look at the test for divergence. The test for divergence tells us that if an does not converge to 0, then the series diverges. The same way that if you're thinking about area underneath the graph of a function, if this area is a finite number, then the function would have to go to 0. And this is called test for divergence. So if you can show that an doesn't converge to 0, then we can show that sum of an diverges. But if an does converge to 0, that does not mean that the sum converges. It could be convergent, it could be divergent. So from pre-calculus, we know that the sum of the terms of a finite geometric series is evaluated by first term minus term after last term divided by 1 minus common ratio. So let's use that to solve this problem. Determine when this geometric sum converges. First of all, let's look at the nth term of this. What's the limit of that as n goes to infinity? Well, we talked about this last time. Well, this is 0 if r is between -1 and 1. It is 1 if r is 1, and it does not exist otherwise. So by the test for divergence, in the second and third case, the series diverges because the limit is not 0. So if r is greater than or equal to 1 or r is less than or equal to -1, then limit of Rn is not 0. Either it is 1 or it doesn't exist. So by the test for divergence, the series diverges. The sum of r to the n diverges. N equals 1 to infinity. Now let's see what happens if r is between -1 and 1. So that may or may not converge. We'll have to see. So suppose r is between -1 and 1, and let's see what happens. We will have to take the partial sum. So we'll take the sum n equals 1 to m of r to the n. This is a geometric sum, so the formula is the first term minus the term after last. The last term is r to the power of m, so the one after that would be r to the power of m plus 1 divided by 1 minus common ratio. Now let's take the limit of this one. So the limit of r minus r to the power of m plus 1 divided by 1 minus r as m approaches infinity is r minus, well, because r is between -1 and 1, r to the power of m plus 1 approaches 0. And 1 minus r is constant. So this infinite sum is in fact r over r, 1 minus r. Okay, so in general, if you have a geometric sum converges if and only if precisely when the common ratio is between -1 and 1. And we're going to have to assume that the terms of this geometric sum are not 0, because if they're all 0, then the sum is obviously 0. And the sum is evaluated by a over 1 minus r. One thing that we need in order to be able to evaluate these sums is some rules of summation. Sum of an plus bn is sum of an plus sum of bn. So you can split up your sum into two different sums. And if you have a constant, you can take it out. You can factor the constant. Let's use that to solve one problem. So we want to evaluate this sum. So let's take this sum and break it up into two pieces. These two pieces, 7 to the power of n, 10 to the power of 2n, and 8 to the power of n plus 1 over 10 to the power of 2n. These two pieces are both geometric sums. So we can easily evaluate them. Well, what's the first one? The first one is 7 over 100 to the power of n. So that tells us that each time the terms are multiplied by 7 over 100. What about the next one? The next one is, if we factor one of the 8s, 8 over 100 to the power of n. So that is also a geometric sum. So if the common ratios are less than 1, we have the formula. If the common ratio is more than 1, then they do not converge. So if you look at 7 over 100, this is between -1 and 1. And 8 over 100 is also in the same range. So the formula for the geometric series can be used. And if we use that, what are we going to get? We're going to get the first term. So in the first sum, the first term is 1 over 1 minus common ratio, which is 7 over 100, minus in the second term, the second sum, the first term is 8 over 1 minus 8 over 100. And we can simplify this. We get 100 over 93 minus 800 over 92, and we can simplify this further, but that would be basically the answer to the question. Okay, so next example. This would be the last example, and then we will summarize what we have done in this video. Determine if this series converges. If we take a look at the terms of this series, and we take the limit n sine of 1 over n, well, what's the form of this limit? The form is infinity times 0, because sine of 0 is 0. So we can use L'Hopital's rule to figure out what the limit is. If the limit doesn't exist, or if the limit is not 0, then we can say the sum diverges. Let's try that and see what we get. So that's the limit as n approaches the infinity, sine of 1 over n divided by 1 over n. Now this is 0 over 0, so we can apply L'Hopital's rule, and what we're going to get is the limit as n approaches infinity. Sine becomes cosine when you differentiate. Derivative of 1 over n is negative n to the power of negative 2, and we have the exact same thing at the bottom. So these two in fact do cancel. As n goes to infinity, this is going to become cosine of 0, which is 1. Now because this limit is not 0, by the test for divergence, the series diverges. So by the test for divergence, the series diverges. And that is what we wanted to do. So to summarize, what we did was we know that the infinite sum can be found by taking the limit of partial sums. Partial sum is the first few terms of a series. If we have a geometric sum, we can evaluate that as long as the common ratio is between -1 and 1, and the formula is the first term divided by 1 minus common ratio. Otherwise, it diverges. When terms of an infinite series are rational functions, the series can often be evaluated using the method of partial fractions. Test for divergence states that if an does not converge to 0, then the sum diverges, although it doesn't tell us anything about what happens when an approaches 0. If an approaches 0, then the series may converge or may diverge. And that brings me to the end of this video. I will see you in the next video.